to do is a mixture of paper 1 and paper 2 today, but I want to go back to paper 2 because I know that that's the one that generally throws us more than paper 1. So what I'm going to do is I'm going to start with calculus and just talk about some of the things that we need to make sure that we know. Take screenshots. I am going to make notes on the diagrams, etc., and then we're going to practice some questions and yeah, see where we go with all of this. Okay, so for the calculus part of your paper, the thing that you need to focus on, you don't need to worry about limits too much, but you do need to make sure that you are able to do first principles. Okay, make sure that you know your rules for differentiating and that you know what you're doing when it comes to derivatives and tangents, because those are always asked. In the first sort of hint when it comes to calculus, it says here, make sure you use the correct notation for first principles. All right, so for first principles, we've got to make sure that we use the correct formula. This is it over here, all right, and that is on your formula sheet. All right, just a couple of little hints of when we are working with first principles is make sure that you use brackets. Okay, especially if f of x has two terms in it. Okay, so use brackets, especially when differentiating from first principles. All right, the other little hints that I want to give you over here, all right, is don't drop your limit notation too soon. And the other thing that we've got to be careful of is do not show that h equals 0. Okay, because you're going to be penalized for those things. Okay. Any other questions about first principles before we move on? All right, moving on then. No, okay. All right. The next thing that we need to be careful of is our notation when we are working with the rules. Okay, so in other words, if they give us a function in the form y equals, only when we apply your power rule do you then write dy over dx. Okay, if they give you your function in f of x notation, it's only when you apply your power rule that you write f prime x. Okay, and again, if they give you your function notation, no, sorry, Kit Kat. Sorry, my cat's just jumped up here now. If they give you your function notation using dx and square brackets, remember in the line where you apply your power rule, that's when you drop the dx, you drop the square bracket, and you just write equals. Okay. The other thing you need to be aware of is applying your laws of exponents correctly. So in other words, when you multiply like bases, you add exponents. When you divide like bases, you subtract your exponents. If you need to raise a power to a power, then you multiply your exponents. If you have got a bracket with two terms in it that's squared, make sure you use FOIL to get rid of the brackets. And then the other thing that you've got to be aware of is what to do when you have got roots. Okay, so you need to remove all roots before you differentiate. So for example, if you have got the cube root of x to the power of 4, remember the guy on the outside gets bounced, or the guy at the bottom, sorry, let me just get rid of the cat here. No, kitten. Dale. Oh, there we go. Sorry, the cat's just, come, move. Sorry, my cat's just creating issues here for me. the guy at the bottom gets bounced to the outside of the party. So when you are removing your roots, you would put your 4 in the numerator and your 3 at the bottom. Okay, if you are going to manipulate something using algebra, make sure you use correct algebraic manipulation. You can only add and subtract like terms, etc., etc. Moving on to the cubic function, make sure that you know the difference between a function f of x and its derivative f prime x. So f prime x is the gradient at a particular point. So let me just put a little bit more about that on the side over here. We were speaking about this the other night in our functions course. Just go over here. So remember, we use function notation for y. So a function is f of x, and we can also describe that in terms of y. That is our output. If we write f prime x, that's no longer y, that is now gradient at a particular point. Okay, so the symbol for that could also be an M. And if we've got f prime prime x, then we are now talking about a graph's concavity. Okay, so things to be aware of there. You also need to make sure that you understand the concept of concavity. Do you want me to go through concavity again and what it means? Can I explain concavity again? Sure. Okay, not a problem. So let's again go onto the side. Okay, and let's draw ourselves a cubic function. All right, so let's pretend we have a cubic function that does that in shape. Okay, so remember your cubic function is characterized by up to 2 turning points. At the turning points, the graph changes direction. Okay, at the turning points, there is nothing happening to gradient. Okay, so we would say that f prime x is equal to 0 at our turning points. Your concavity changes at your point of inflection. Okay, so your point of inflection is halfway between your turning points if you've got 2 turning points. Okay, so you can either calculate your point of inflection, the x coordinate at your point of inflection, using f prime prime x equals to 0. Or if you have the coordinates at your turning points, you can use midpoint formula. Okay, not midpoint theorem, midpoint formula. All right, so in this particular function over here, this is where a is negative. So the a in front of your x cubed term. When the graph is like this is referred to, so the purple bit that I'm coloring in at the moment. The purple bit is what is referred to as concave up. Okay, so here, let's just see if I've got something that's more purple. No. Okay, so here the graph is concave up. So that's when it's cup shaped. All right. After your point of inflection, so where the pink is over here, this is where your graph, this is where your graph is concave down. Okay, so let's get a pink pen. This is where the graph is concave down. Right, and they often ask questions, for which values of x is the graph concave up? Or for which values of x is the graph concave down, for example. Okay, so you would need to know that. All right, so if I just continue here on the side, let's pretend that we have a cubic function that's first concave down and then concave up. Okay, so in this particular one here, A is positive. Your point of inflection would be somewhere over here. Okay, it is first concave down and then it is concave up. So let's pretend that we have calculated the x coordinate at the point of inflection. So for the graph on the left, let's pretend our point of inflection is where x was equal to 2. Let's just pretend. I'm just making that information up. Okay. If they said to you, for which values of x is the graph concave up? I'm just going to type that. For which values of x is the graph of f concave up? I don't know if that's big enough for everybody to see. Let's just make it a little bit bigger. You would say for the graph on the left, the graph is concave up when x is a number that is smaller than 2. If they said to you for which values of x is the graph concave down, again with the graph on the left, let's just copy that. You would say where x is smaller than 2. Sorry, where x is greater than 2, beg your pardon. Where x is greater than 2. So remember, your x-axis is your horizontal axis. So it doesn't matter where your x-axis is. If that was your x-axis over there. So numbers get bigger as you move to the right. Numbers get smaller as you move to the left. All right, so that's why we would say if x was equal to 2 at the point of inflection, the graph is concave up when x is smaller than 2, to the left of the point of inflection. To the right of the point inflection, those are the values of x for which the graph is concave down. And it would be the other way around for a graph where A was positive. Okay, so if over here, let's pretend our point of inflection is where x was equal to 1, it would be concave down where x is smaller than 1. It would be concave up where x is greater than 1. Okay, so concave up and concave down can also be written in another way. All right, so concave down, they can also write like this. So concave down can also be written where f prime prime x is smaller than 0. Let's just move over a little bit here. That's concave down. So f prime prime x is smaller than 0. They can also describe concave up as f prime prime x is greater than 0. Okay, so that's using words and then using notation as well. Okay, Nawazi, where do you want me to scroll to? Is it all right where I am? Right. So I'm just going to continue talking. As far as gradient, you got it. Oh, good. Okay. So as far as gradient is concerned, they could describe gradient like that. And then you need to know that this means gradient. So when they do that, they're talking about when the graph is increasing or the gradient is positive. If they go f prime x smaller than 0, they're talking about where the graph is decreasing. Okay, so in other words, gradient is negative. So always think about gradient as walking uphill or walking downhill. When the gradient is positive, so f prime x is greater than 0, the graph is increasing, you are walking uphill. Okay, if the gradient is negative, f prime x is smaller than 0, then the graph is decreasing. You are walking downhill, always from left to right, okay, as x gets bigger. Okay, matrix, everybody happy with that? Any questions?
Take screenshots, but you
Yeah,
guys are
so
doing well.
and of course, you know, if there's any sort of point that you want to come back to or whatever, you can always watch the video again and then just stop it in the appropriate place. All right, but yes, please do ask questions if you need to. And then the last point that I wanted to make sure that you know that there are two ways for finding the point of inflection, which I have mentioned to you. Okay, so the first way is by taking the second derivative and making it equal to 0. The other way is to use midpoint formula. Okay, so either way. All right, and then if you are working with first derivative to find the coordinates at the turning points, make sure that you let it equal 0. If you're working with the second derivative to find the x coordinate at the point of concavity or the point of inflection, rather make sure that you show that f double prime x is equal to 0 as well, because you get marks for those zeros. All right, that's very, very important. Okay, so those are my hints and tips with regards to calculus and as far as we've got now. What I'm going to do is I'm going to move on, if there are no questions, and talk a little bit more about trig, because I've got quite a lot of tips and hints to share with you as far as trig is concerned. Trig is obviously one of our biggest sections. At the end of the year, in paper 1, calculus is 50 marks, and that will be the same for trials. And in paper 2, trigonometry is the biggest section. Okay, so it's also 50 marks. That would be the same for trials. Obviously, now for your June papers, it's a little bit different, the mark allocations, but trig would probably still be the biggest part of paper 2, and calculus the biggest part of paper 1. Okay, so as far as my tips and hints for trigonometry are concerned, let's get started on that. That's fine, Lebogang, welcome. We've just got a small class, there's only 39 of us here today. All right, so the first little bit of information that I want to give you is make sure you know all your formulae, okay, especially the ones that are not supplied on your formula sheet. Okay, so which ones are supplied on your formula sheet? Well, I don't know if we need to worry about it now. We don't have to, I haven't included the sine rule, the cosine rule, and the area rule, but these are the ones that are provided there. So these are our compound angle formulae, right? So that's these ones up at the top over here. These are our compound angle formulae that are supplied to us. And the other thing that they give us are our double angles. Okay, so be particularly careful when working with your compound angle formulae. I cannot tell you over the years when I have marked matric papers, it's really, really upsetting to see a candidate has used the wrong compound angle formula, okay, or hasn't copied it down correctly, or has learnt it but hasn't learnt it correctly, etc., etc. If you're going to learn them off by heart, it's obviously going to make it easier for you because you're not going to have to move backwards and forwards. If you can detach your formula sheet, then ask to do so, because then at least you've got it on every single page that you are working. All right, so be very careful when you're working with your compound angle formulae. Either learn them correctly or make sure that you copy them correctly. Okay, because if you don't use them correctly, you're obviously never going to get any marks for anything. Right. So if we give us our compound angle formula and our double angles, which rules am I referring to that are the ones that are not supplied on your formula sheet? What are we talking about specifically here? What formula am I referring to? Think grade 11. So I'm talking about your tan identity. So tan theta. Yeah, so SOHCAHTOA, sure, fair enough, Nolwazi. But specifically, I was referring to your tan identity. So in other words, tan theta can be written as sine theta over, beg your pardon, cos theta. The other one that I'm referring to is sine squared theta plus cos squared theta equals 1. That's your square identity. All right, so those are not on your formula sheet either, but they still come up. Okay, so you would still be expected to be able to use those. Remember, we can further manipulate our square identity. So what we can do if we want to is we can make cos squared theta the subject to the formula by moving sine squared theta over to the other side. Okay, and then this becomes a difference of two squares. So if you needed to, you could factorize it further, couldn't you? All right, so if you wanted to, if you needed to, you could factorize it to 1 minus sine theta, 1 plus cos theta. Okay, and the same thing can happen with sine squared theta as well. Okay, so just moving over here, if I make sine squared theta the subject of the formula, that could be written as 1 minus cos squared theta. And if you needed to, you could factorize that as well. So 1 minus cos theta, 1 plus cos theta. Right, so those are not going to be on your formula sheet either. You need to know them from grade 11. Okay, the other thing that is important when you're working with trig is check that your calculator is in degrees. Okay, if you work in radians, you are going to get completely the wrong answer. If you have got a Casio calculator, you can do this. Let's just move Yolanda out the way. All right, so on a Casio calculator, most of us have got Casios. Okay, what you would do is you would turn your calculator on, right? Then you would press Shift 9. I'm going to write this down for you. So you would press Shift 9, then you press 3, then you press equals, and then you press AC. And what this does is it resets your Casio, it resets your calculator. Okay, and then it will automatically make sure that it is in degrees and not in radians. Okay, so before you write paper 2, before you do your trig section, make sure that you have reset your calculator. If you see an R, you should see a little D at the top. If you see an R or a G, then that is a sign that you need to go and reset it. There must be a little D up at the top. Okay. Otherwise, you're not working in degrees, you're working in radians or something else. Okay, so the other thing that you should also give a lot of thought to, right, is how your plan for your exam. All right, so for example, what you could do, because trig is the biggest section, is make sure that you go and do your trig first, right? In maths, really, the idea is to find the questions that you feel competent with and you think you know how to answer and go and ask those first. Right, and then come back to the things that you don't know. What you need to be able to do is you need to be able to recognize the questions that you've been taught in class or that you've done here at Watobe and focus on those. Okay, there are always going to be questions that everybody is supposed to answer. Our level 1, level 2 questions, the things that have been done in class. You need to recognize them, look for them, go and do those first. And then if there is something that you don't know how to do, then highlight it or make a note of it and come back to those afterwards. Okay, all right. I'm just having a look at the chats here. You can also use shift mode, then number 3. Thanks for that, Nazole. I hope the rest of us saw that. Keith Lynn, don't worry about being late. I know there were a couple of Lebogang was also late. It's not a problem. What I'm doing is I'm talking about tips and tricks for the exam. If there's time at the end, then I'm going to try and do some questions with you, but I'm just basically going through tips and tricks for the exam. We've already discussed calculus, and I'm on to trig now. Okay. So decide what you're going to answer first, matrix. Go and do that. Do it well. All right. And then go and worry about the questions that you can't do. The thing is that none of us can do maths if you are upset or anxious. You need to be calm in order to be logical. All right. So you need to think about how you're going to manage your stress and your anxiety. If there are things that you see that you don't know, okay, you have to somehow not let. Please, can you just mute Lesedi? Thank you. Just Lesedi. What is going on with Lesedi today, Yolanda? There we go.
I'm not quite sure. It could be that it's,
Lesedi.
okay.
Okay, there we go. That's
Sort
better.
that out.
There we go. You just have to not let that bother you. Okay, there are not going to be more questions that you don't know how to do than things that you do know how to do, especially if you've been working in class, working at home, attending Watobe. There's going to be more stuff that you know than stuff that you don't. Right. If you see a question that's for 5 marks and you don't know how to answer it, don't worry about that. You don't need to do every difficult problem solving question in order to do well in the paper. You can still leave out all the problem solving and get an A. All right, if you can do all the other work correctly. Okay, so don't worry about problem solving. Make sure that you can do the level 1 and level 2 questions. Okay, so the things that you recognize. Okay, another important thing in trig, don't make up rules. Okay, so don't make up stuff that doesn't exist just because it seems appropriate to you at the time. That's something that happens a lot. Make sure that you show all your steps. Okay, it's better in maths most of the time. More really is more. You're not necessarily going to get marks for all the steps, but it's better for you to show how you got something rather than just write answers down. If you write down just answers, you're definitely not going to get full marks. As far as trig is concerned, when I say show all steps, make sure that if you use reduction formulae, you show what you get when you were reducing. Okay, so show your answer. Sorry, your answer when using reduction formulae. Okay, if you have to rewrite tan theta, sine theta over cos theta, show that step. If you have to rewrite 1 as sine squared theta plus cos squared theta, show that step. Okay, these are the things that I am referring to. Okay, so for the level 1 and level 2 questions, how many marks are there? So any paper, any maths paper, whether it's paper 1 or paper 2, let's just scooch over to the side here, is always set in the same way. All right. So your knowledge questions always have to be 20% of your paper. Your routine questions are always 35% of your paper. These are your level 1. This is level 1 and this is level 2. So these are your easy questions. Okay, so when I say easy, I mean this is the stuff that you've been done in class. It is the things that you have been taught. These are the things that absolutely everybody is supposed to be able to do. Okay, that's 55% of the paper. All right. Then it comes to your more difficult questions. So now level 3. Level 3 are your complex type questions. So your complex questions. So this might be a question, for example, where you have to integrate information. So for example, let's say that you are doing analytical geometry, but you could use trig to answer a question because you were working in a right angle triangle. That's a complex type of question. Let's just see if I've got any other examples of something that's complex. That's not complex. Okay, so if we have a look at this question over here, all right, they've given us a diagram. There's quite a lot going on in the diagram, etc., etc. If they say to us, explain why FC is parallel to GH, that's knowledge. Then when they say to us, calculate with reasons the length of DM, if there's no clear place where to start, then that would be a problem-solving question. So that's potentially problem-solving. It could be complex, right? If we have a look at something like this, so they've given us a circle, the question says, prove that MC is a tangent to a circle, all right? That would probably be either difficult routine or easy complex sort of question. Then the next one, proving that the triangles are similar to one another, that would be seen as a routine sort of question. Okay, so complex questions are ones that have got a few more steps, maybe where you have to work backwards, etc., etc. Those are 35% of your paper as well. Okay, so the easy bits are supposed to be 55% of your paper. Your complex questions make up another 35%. Sorry, I'm talking nonsense. It's 30%, not 35. Sorry, beg your pardon. It's 30%. And then your level 4 questions. Okay, this is your problem solving. Okay, and we know problem solving when there is no clear place where we need to start. We don't know how we're supposed to approach this problem. It is application of our basic information, and sometimes we have to work across more than one area. So we might have to use trig, for example, in analytical geometry, or we might we have to think out of the box, etc., etc. No clear place where to start. That's 15% of your paper. So you know how much your June exam is going to be out of. These account for 45% of your paper. So 55% of your paper is meant to be dead easy and straightforward and routine, and the other 45% of your paper is supposed to be your slightly more challenging questions. All paper ones and paper twos have to be set according to these levels. Okay. All right for you, no problem. Thanks for your question. So let's go back to trig. Okay, so use correct algebraic steps. So when I say use correct algebraic steps, I'm really referring to things like if you say sine theta plus sine theta, that's 2 sine theta. Or if you've got cos theta times cos theta, you would write that as cos squared theta. Make sure that you factorize correctly. All right, so treat sine theta and cos theta like they are variables. So if you have sine theta cos theta plus sine theta cos theta, it's like having xy plus xy. That would give you 2xy if you added them together. So if you've got sine theta cos theta plus sine theta cos theta, you've got 2 sine theta cos theta. Right, so your algebra always related back to what you know. The other thing that you've also got to make sure is that if you are given a bracket, so for example, let's say you've got a bracket and you've got sine theta plus cos theta, and that's been squared. Using the correct algebraic steps means, for example, when you are squaring a binomial, okay, you're not just squaring the first term and squaring the last term. You've got to think about FOIL. So in other words, that's a common mistake that comes up. Okay, you're doing FOIL. All right, so use the correct algebra, firsts, inners, outers, lasts. Okay. Then it says, make sure you know all your grade 11 as well as your grade 12 trig. Okay, so the grade 11 trig is really important. Make sure that you have learned all your reduction formulae, including your negative angles and your co-functions. Do you want me to do a brief summary of that with you? Do you want me to do a brief summary of all your reduction formulae? I can, if you'd like. Yes? Okay, cool. All right, so let's go onto the side over here, right? And we'll just talk about the cast diagram as well. Okay, so our grade 11 trig is vital. We cannot do grade 12 without it. Okay, cool. All right, no problem. So let's get ourselves a Cartesian plane. Oh, hang on a second. Let's use a better pen. There we go. Okay. All right. So when it comes to your grade 11 trig, okay, this is your x-axis. This is your y-axis. This is quadrant number 1, where x is positive and y is positive. This is quadrant number 2, where x is negative but y is positive. This is quadrant number 3, where they are both negative. And this is quadrant number 4, where x is positive but y is negative. Furthermore, we have decided that this is 0 degrees, this is 90 degrees, this is 180 degrees, this is 270 degrees. When we are working in quadrant 1, angles are acute, so theta would be an acute angle, and we can also use the reduction formula 90 minus theta for the first quadrant. Okay, so imagine that your terminal arm is, so where do negative angles come from? When our terminal arm is anchored at the origin. Okay, so I'm going to draw terminal arm. Terminal arm is anchored at the origin like the hand of a clock. Okay, and it can spin. So if it goes in that direction, which is anti-clockwise, angles are positive. If your arm moves in this direction, that's where we get negative angles from. Luzo Kubanda, Bam, your screen is black. Yolanda, can you just help? I don't think my screen is black. All right, so imagine the terminal arm is anchored at the origin. We go 90 degrees in an anti-clockwise direction and theta degrees in the other direction. That is why 90 minus theta is quadrant number 1. In quadrant number 2, we use the reduction formula 180 minus theta because again, our terminal arm is anchored at the origin. We go 180 degrees in an anti-clockwise direction and theta degrees in the other direction. Okay, you can also use 90 plus theta, but I'll talk about those just now. For the third quadrant, we use 180 plus theta. So again, our terminal arm's anchored at the origin. We're swing 180 degrees in an anti-clockwise direction and theta degrees forwards into the third quadrant. And if we're working in quadrant number 4, we use 360 minus theta. So we've done a full circle and then we've gone theta degrees in the other direction. Okay, so now based on our signs of our coordinates, remember, all right, sine theta is y over r. Cos theta is x over r. Tan theta is y over x. Okay, so that's why when we are in, let's just scooch over a little bit more. Okay, when we are in quadrant number 2, okay, x is negative and y is positive. So that's why the sine of 180 minus theta reduces to positive sine theta. The cos of 180 minus theta reduces to negative cos theta. The tan of 180 minus theta reduces to negative tan theta. Okay, so because cos theta and tan theta have x in them and x is negative, that is why cos theta and tan theta are negative in quadrant number 2. So basically what I'm really explaining to you here is your cast diagram, C-A-S-T, like so. Okay, in quadrant number 3, remember both x and y are negative. So the sine of 180 plus theta gives us negative sine theta. The cos of 180 plus theta gives us negative cos theta. All right, the tan of 180 plus theta is negative divided by negative. Negative y over negative x. That's why it gives us positive tan theta. Quadrant number 4 now. X is positive, y is negative. So the sine of 360 minus theta is negative sine theta. The cos of 360 minus theta, quadrant 4 where x is positive, cos theta, positive cos theta. And the tan of 360 minus theta gives us negative tan theta. Okay, so I'm also just going to add onto this diagram over here, x and y change sign depending on quadrant. Okay, r is a length. Okay, it's the length of the terminal arm. Or you could also view it as the length of the hypotenuse. So therefore it is always positive. Okay, so r is always positive because it is the length of the terminal arm. Okay. All right, so let's just talk about negative angles because we haven't got those over here as well. All right, so in other words, so a negative angle, what's happened is that instead of your terminal arm moving up, so if that's theta over there, your terminal arm has moved in the opposite direction. So that would be minus theta over here. The idea behind negative angles is this. 0 degrees and 360 degrees are in the same position. You've done a full circle in an anti-clockwise direction. Okay, so 0 and 360 are in the same position. Let's just move over. Talk about negative angles. Okay. All right, so 0 degrees and 360 degrees are in the same position. So that means that 0 minus theta is the same as 360 minus theta. Okay, so that is why we consider negative theta means the fourth quadrant. Okay, so they can give us sine minus theta, that reduces to negative sine theta, or cos minus theta, this reduces to positive cos theta, or tan minus theta, this reduces to negative tan theta. That is because sine theta and tan theta are negative in the fourth quadrant. Okay, because that is where y is negative. Cos theta is positive because x is positive and r is always positive. Okay, so that's the deal with negative angles. So you can look, going back to your cast diagram again, okay, you can look at 270 as negative 90. Okay, I'm going to say that again. You can look at 270 as negative 90. Okay, for example, right, negative 180 degrees, you're in the same position, because if you go plus 180 or minus 180, 180 is always going to be a straight line. Okay, so negative angle simply means that the terminal arm is swinging in the opposite direction. It is swinging in a clockwise direction as opposed to an anti-clockwise direction. That's where we get negative angles from. Okay, and negative angles are easy for us to deal with. If we have to deal with negative angles, then generally the rule of thumb is we would add 360 or multiples of 360 because we would end up in the same quadrant. Okay, you never thought about it like that. I know this is where Watobe is I think really important. The other thing that I want to show you at this point, something else you probably haven't considered, which now that you're in matric will also, I hope, and remind me, I do need to come back and talk about our co-functions because they're also important. Can you see how much learning there is with trig? Trig is just studying, 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 studying. You've got to learn all of these things. Okay, so the other thing that's also important for us to consider is look at it like this. Okay, so I'm drawing a set of axes, not very well. I've hurt my thumb today, so I'm not writing very nicely. I'm going to draw a sine graph. Come on. I'm going to draw a sine graph. There you go. So our maximum would be at 90. We've got an x-intercept. We've got a minimum at 270. And we've got 360 over here. So the other way that you can look at it is that over here, this is quadrant number 1. Okay, over here, this is quadrant number 2. Over here, this is quadrant number 3. Over here, this is quadrant number 4. Okay, so when we say that sine theta is positive in quadrants 1 and quadrants 2, it's because your ratio, your y value, your output value is a positive number. The graph is above the x-axis. Okay, so when you see something like sine theta, come on pen, is equal to 1 over 2, this number over here, your ratio, that is your output on your graph. Okay, so for example, at 30 degrees, if that was 30 degrees over here, then that would be equal to 1 over 2. All right, so that's why we say that sine theta is positive in quadrants 1 and quadrants 2 and negative in quadrants 3 and 4 because the graph is below the x-axis. Sorry, just give me a second. Cat, come. Come here, kitty cat. Come. Come, darling. Sorry, I don't know what's wrong with him today. He was away from home and now he's crying.
No worries, no worries,
Sorry,
Teacher
guys.
Lee. I'm
All
also
right. So,
having Nathan on my side, so don't worry.
oh, are you?
I
Okay.
understand.
Yeah, well, your son is more important than my cat. But I just don't want him to go and meow and bother people. It's cool, hey, it's Echofatso. So you see how it all comes together. And it's exactly the same with your cos graph. Okay, so if I was to draw a cos graph here, let me just draw it over this one instead of drawing a new one. Then let's say that 1 is there and okay, I haven't drawn this very well. -1 is over there. Your cos graph. Sorry, guys, that's a really amateur cos graph. But if that's your graph, y equals cos x in yellow, and we said the purple one was y equals sine x, can you see it's the same thing? All right, so looking at the yellow graph now, matrix, the yellow one, let me just highlight it to make it stick out a little bit more. Okay, can you see that your cos graph, your outputs on your function are positive in quadrant 1. They're negative in quadrants 2 and 3 because the graph is below the x-axis, and it's positive again in quadrant 4. Okay, so this informs our cast diagram. In my opinion, it's when you start looking at the graphs like this that your general trig starts to make sense. Okay, and then the same thing would happen with your tan graph. So remember there are asymptotes at 90 and 270. So your tan graph would do, let's do it in orange. Your tan graph would do that. and it would do that, and it would do that, and then it would do that. Okay, so the orange, let's just see if I can get an orange highlighter. There we go. Let's just make that a little bit. Can you see again? Your tan graph is above the x-axis in quadrant 1, below the x-axis in quadrant 2, above the x-axis in quadrant 3, below the x-axis in quadrant 4. Okay, so this helps to inform our cast diagram. Okay. Your teachers didn't, so that's where graphs come in, absolutely. Okay. 100%. And guess where angles are negative, guys? To the left of the y-axis. Okay, so you're just spinning in a different direction. Okay, so there's negative 30 and there's negative 60, etc., etc. So you've just got to look at it from a different perspective. Okay, so yeah. Oh, I so appreciate that. You see, it makes a big difference if your teacher understands what they're doing, then it makes a big difference in how they explain things to you as well. So hopefully there are lots of connections going on today and things that are falling into place. It's a pleasure, Nolwazi. It is super cool, isn't it? It's really nice to see actually where everything fits in because you often wonder like what is a cos graph? What does it mean? How is it connected to the general trig that I'm doing? And now here you can see your cast diagram in front of you. Okay. Yeah, sure. Is there a question? Oh, shame, Tunda. But you know what? I'm going to be here with you the whole way through the year. Okay. The whole way through the year, right up until you write those final papers. Okay, so you just keep coming to Watobe and then you can ask questions. And I'm going to do as much of this with you as I possibly can, try and explain how things are connected and what it all means. All right, there was a question. Who wanted to ask? Lebogang. Go for it, Lebogang.
Ma'am, I wanted to ask about plotting the graphs, ma'am. Are the critical points 1, 0, and -1 when you're plotting the graph?
Not on a sine, cos, or a tan graph. No, on like a straight line function, then yes, but not on a cos function. Because remember, on a cos function, your inputs are not -1, 0, and 1. They're degrees. So it depends which graph you're drawing. If it was a trig function graph, then you would use things like 30, 60, 90, etc., or 45, 90, whatever the case might be. It obviously also depends on what your period of your graph is, etc., etc. Okay. All right. So let's go back to this diagram over here. The problem with a lot of this when we teach it is that maths seems very flat and it seems very static. It's not. It's three-dimensional and it's fluid. Things move. If you think about functions, they move them. They move them left, they move them right, they move them up, they move them down, they reflect them. All sorts of things happen like that. Think about your cast diagram as three-dimensional. So imagine where the origin is. You know what a slinky looks like? You know those slinkies that we all played with when we were little? See the origin as a slinky string. And your terminal arm sits on the outside and it twists around like this. And when you go forward, that's the anti-clockwise direction that moves you to the right. When it goes in a clockwise direction, the terminal arm is twisting backwards and it moves to the left where angles are negative. Okay. All right, so that's our reduction formulae. That is our negative angles. Let's just talk about 90 plus and 90 minus. Now, there are very good reasons why these change. I'll just show you 90 minus for now. 90 plus, in order to understand why 90 plus gives us, well, cos 90 plus gives us minus sine theta, and sine 90 plus theta gives us cos theta, we need to understand a rotation. You don't need to know about that though. That's never going to be asked. But maybe your teachers explained this to you. This is where 90 plus and 90 minus comes from. Okay, so I'm now talking about co-functions, and then I'm going to go back to the graph for this as well. So here is an incredibly badly drawn right angled triangle. If I call that side A and I call that side B and I call that side C, then that would be angle A, that would be angle B, that would be angle C over there. If I say that this angle over here is theta, how big is angle C in terms of theta? How big is angle C in terms of theta? Can anybody tell me? There we go into causal. Well done. It's going to be 90 minus theta. So remember, the angles of a triangle add up to 180 degrees. So if you add C and 90 and theta, C and 90 and theta, you get 180 because of angle, sum, and triangle. And that's why we've got C is equal to 90 less theta. Okay, so this is 90 less theta. Okay, so this links back to our co-functions. If I talk about the sine of theta, I'm using theta as my reference angle. So in a right angle triangle, it would be opposite over hypotenuse. That would give us B over A. Now we're going to change our reference angle. So instead of using theta, I'm going to use 90 minus theta as my reference angle. So if I use the cos of 90 minus theta, the cos of any angle is adjacent over hypotenuse. So that would also be B over A. All right, that's why the cos of 90 minus theta is equal to sine theta. It comes from a right angle triangle. Okay, so, and it would be the same the other way around. Okay, if you looked at the cos of theta, it would be adjacent over hypotenuse. If you look at the sine of 90 minus
Hello, ma'am.
theta, that would be opposite over hypotenuse. Hello, who's
Hello,
talking?
ma'am. It's Shofato.
Hello, Tegofatso, how are you?
I'm good, and how are you, ma'am?
I'm fine, thank you. Do you want to ask a question?
Yes. So
Go
with this
for
type of principles, would they ever ask us questions based on like the how this cosine rule is formed and stuff like that?
No. They're not going to ask you where it comes from. I'm just explaining to you where it comes from.
Oh, okay.
Okay. All right.
Okay.
So, but you need to know what I'm writing in blue. That's what you need to know.
Oh, okay.
Okay.
Thank
All
you.
right. No problem. And then your other co-function, which, you know, if there is time for us one day for me to explain to you where it comes from, this is sine 90 plus. So that's the second quadrant. Okay, so it becomes positive cos theta. And then we have also got the cos of 90 plus theta. It's second quadrant, where cos theta is negative. So your outcome takes the answer of that function in the original quadrant. So the original function in that quadrant. So because cos theta is negative in quadrant 2, that's why we end up with negative sine theta as our answer. Okay, so those are your co-functions. Right, very important. They get asked a lot in matric, especially when it comes to numbers. So for example, if you have got the sine of 20 degrees, you must also think about it as the cos of 70 degrees, for example. Or if they give you the cos of 55 degrees, you've got to think about that like it's the sine of 45 degrees. Oh, sorry, that would be 35 degrees, not 45. It's got to add up to 90. Okay, so very important for matric, right, is being able to rewrite sine theta as cos theta and cos theta as sine theta. Okay, as I said to you, I could explain where 90 plus comes from, but it involves a rotation. You don't need to know that, but you do need to know what the sine of 90 plus theta and the cos of 90 plus theta are equal to. Okay, matrix. Let's just go back and make sure that we have done everything here that I can think of. Negative angles, 90 plus, 90 minus, etc., etc. Okay. All right. So let's get back to what we were discussing over here. Another thing that's really important in your section on trig, you are doing general trig, you are not allowed to use a calculator. So do not ignore instructions where it says without the use of a calculator. So if you are doing, let's say, the theorem of Pythagoras, and you have 25 squared minus 7 squared, and you want to work out what the answer is, you can use your calculator for that. All right, but when they say without the use of a calculator, they generally mean that you need to use all your, you need to show all your steps, and you are not calculating the size of theta. Okay, all right, then the other tip that I have given you is to learn all your reduction formulae and know which formula to use in a given situation. So if you had an angle that was, let's say, obtuse, so let's pretend they gave us, or we ended up with the cos of 135. We need to know that 135 is the second quadrant. So we would either need to use 90 plus if we wanted to, which would be a little bit more difficult, but we would use 180 minus. Or if they gave us something like the sine of 225 degrees, we need to know that 225 is between 180 and 270. We would use 180 plus. If we had an angle that was, for example, the tan of 315, we know that 315 is bigger than 270 but smaller than 360. We've got to use the appropriate reduction formula, which would be 360 minus. Okay, and then be aware of your cast diagram and what sign your answer would take. Okay, so when I say sign, all right, I mean S-I-G-N. Okay, so be very, very, very careful about your signs when it comes to working with trig. Okay, and again here, I've said be aware of the quadrants when determining the signs of your trigonometric ratios. Okay. This sort of information is good if you are working with the sine and the cosine rule. Oh no, I think I've done, sorry. I don't think anybody's doing sine rule, cosine rule now in June, or are you? We haven't done any work on that yet. You are. Okay, all right. So it just depends on where you are first. Again, these are just, it's really just more or less the same thing. In that case, you would also use, let me just hang on a second. Let me just go up here. So if you are doing 3D trig now, sorry guys, or 2D trig, then you would also need your, let's just grab them here for you. You would need these. Let's just get it and put it on the page for you. Okay, so that would be given to you as well. All right, so these are your trig formulae for area rule, sine rule, and cosine rule. Okay, so the first one over here, that's your sine rule. The second one over here, this is your cos rule. And the third one over here, that is your area rule. Okay, so the important thing to look out for here, or to remember when you're working with these rules, is how triangles are labeled. Okay, so if this is angle A, then the side opposite it will be side little a. If this is angle B over here, then side B is opposite angle B. And if this is angle C over here, then that would be side C over there. When it comes to your sine rule, right, what a lot of people struggle with is, how do I know if I'm supposed to use the sine rule or the cosine rule? There are some questions where it won't matter, depending on the information that has been given to you. And then there are other situations where it is going to matter which rule you use. So if you have got a situation where you have got a side, an included angle, and a side, or three sides. So side angle side means the side over here, the included angle, and that side over there. Or if you've got three sides, so this side, and that side over there, then you would use the cosine rule. Okay, to either work out the length of a side or to work out an angle. Your sine rule works when you have got a side-side angle situation. So for example, if you have this side over here and you have this angle, and you have that side over there, you could then work out the length of that angle over there. Okay, so it's not the included angle. Okay, so not the included angle. Then you would use your sine rule. Okay, so it just depends what you're looking for. Either you can put sine A at the top over A at the bottom, or you can have A at the top and sine A down at the bottom. It really doesn't matter. Your area rule can only be used in a side angle side situation. Okay, so that's a side angle side situation for your area rule. So when they say AB sine C, the reason for that is here's side A, here's side B, and then it's the sine of angle C. So that would be the included angle. Okay, like so. All right. It's a pity actually that we didn't do an example using this. I wish I had known that you guys were doing sine rule, area rule, and cos rule. We could have done an example, but anyway, it doesn't matter. Those generally are not out of a lot of marks. Okay, you did this last year. Yeah, you would have done it in grade 11 for the first time. Okay, all right, let's go on. I'm actually, let me put it with you. What can I do a Euclidean geometry question with you guys? I'll be happy with that. We'll just talk a little bit about Euclidean geometry. Okay, all right, cool. So I want to do a couple of questions with you. So as far as your Euclidean geometry is concerned, you need to make sure that you know all your grade 11 Euclidean geometry. Okay, so that basically gets broken down into 4 parts, your circle geometry. So it's your chord theorems. Okay, so line from center perpendicular to chord, line from center to midpoint of chord. Then when I talk here about your segment angles, these are the angles on the inside of circles. So this is angle at center is twice angle at circumference, angle in a semicircle, and angles in the same segment. So maybe what I should do is write those down. Okay, so your chord theorems are line from center to midpoint of chord, and the other one is line from center perpendicular to chord. Okay, so now the difference between these two, all right, is which one comes with the 90-degree corner. Okay, so here in the first one, let's just get rid of this triangle over there. Here you are not given the 90-degree angle. Okay, from line from center perpendicular to chord, you are given the 90-degree angle. Okay, so just very quickly, if you've got a circle and a chord, and let's say OMBA, all right? So if you are given that BM equals MA, you are not given the 90-degree angle. All right, so you would conclude, for example, that OMA equals 90. Then your reason would be line from center to midpoint of chord. Okay, if you are given a circle and a chord, line from the center, and that's O, that's M, that's A, that's B. Here you are given the 90 degrees. Okay, so here, if you are given that OMB or OMA equals 90, then you would conclude that AM equals MB. Okay, line from center, perpendicular to chord. Okay, so that's how you know the difference between the chord theorems. Okay, so when you are given the midpoints, it's line from center to midpoint of chord. If you are given the 90-degree angle, then it's line from center, perpendicular to chord. Okay, I think that makes it a little bit easier for you guys. I know that a lot of people in grade 11 and going into grade 12 struggle with that. Okay. Then your segment theorems. So your segment angle theorems are a little bit easier. So by this, I mean angle at center equals 2 times angle at circumference. We also include angle in a semicircle. And we also include angles in the same segment. So here, additionally, you also need to be careful. Let's scooch over here. Okay. If you have got a situation where you have got a circle center and you've got something like this. Okay, this is angle at center equals 2 times angle at circumference. Okay, one point, one vertex is in the center, right? Do not get confused with angles in the same segment. So with angles in the same segment, all 4 points are on the circumference. Okay, so can you see the difference here? This point, this point, this point, this point. All 4 points are on the circumference. This is angles in the same segment. Okay, so don't get confused between those two. All right, we need to make sure that we know the difference between them. Okay. Angle in a semicircle. So that was where you have to be given a diameter, a line that goes through the diameter, and then it will subtend a 90-degree corner on the circle. Okay, so that's angle in a semicircle. Like so. Okay, so going back again over here, your cyclic quad theorems. Okay, so there are two cyclic quad theorems. The first one, let's just scooch over again. Let's go over here. When it comes to cyclic quads, a quad is called cyclic because there are 4 points on the circle. So if you have got a quad and it looks like that, sorry, it's automatically cyclic. Okay, so it has to have 4 points on the circle. All right, so there are two things that emerge about cyclic quads. The first one, okay, is that the opposite angles of a cyclic quad are not equal. Okay, they are supplementary. That means they add up to 180 degrees. Okay, so they're not equal. The opposite angles of a parallelogram are equal. Okay, parallelograms cannot be cyclic. Okay, it's not possible to draw a parallelogram and then draw a circle through all 4 points. Okay, so parallelograms are not cyclic. Okay, so the opposite angles of a cyclic quad are supplementary. And the second thing that's very important about this is that the exterior angle of a cyclic quad is equal to the opposite interior angle. So that means that any side of the cyclic quad can be extended. So if I extend this side over here, there's my exterior angle. It would be equal to this angle over here. All right. Or if I extended, say, this side over here, beg your pardon, like that, then here's my exterior angle. It would be equal to the opposite interior angle over there. Okay, so those are generally quite easy. What is a little bit more difficult, okay, are your converse theorems. Okay, so here they will always ask you to prove a quad is cyclic. Okay, so proving a quad is cyclic. What you're doing when you are proving a quad is cyclic is you're proving that it's possible to draw a circle through the 4 points. That's what you're proving when you're proving a quad is cyclic, that it is possible for a circle to be drawn through there. Not that there necessarily is a circle there, but that it's possible for you to be able to do so. Okay, that's what you're doing when you're proving a quad is cyclic. Okay, so you will get some four-sided figure that does not have a circle around it at the moment. And when you prove that it's cyclic, you're proving that it's possible for a circle to be drawn around the 4 vertices of that particular quadrilateral. Okay, there are only 3 ways that you can do this. Okay, and it's converse every single time. That's the easiest way to learn it. All right, so the first one is converse angles in the same segment. And you have to use the word converse. The second way is converse opposite angles of a cyclic quad are supplementary. And you are allowed to use the word cyclic quad because you've used the word converse. And the third way that you can prove that a quad is cyclic is converse exterior angle of cyclic quad. Okay. I did do a course earlier this year where I spoke about proving that quads are cyclic. So if you do want to go and have a look at the Watobe website, then I'm obviously, you know, it would be a good idea. I don't know. Do you want me to? I didn't prepare anything to show you how to prove that a quad is cyclic this particular lesson. Do you want me to do that quickly with you? Would you like me to do an example? I would obviously have to go and fetch something. Yes, please. Okay. All right. Just give me 1 second. Let me just see revision of grade 11 work. Let's see what we can find here. Prove that that's a cyclic quad. So we could do that one over there. Let's just see what else we've got here. Okay, let's have a look at this. Okay, can everybody see this okay? Is it big enough? All right. Okay, so let's have a look at this one. Okay, because this is obviously going to come up for us as well. So when you are doing Euclidean geometry, it is very important, matrix, that you read the information there first. The idea is that when you read the information, you make the connections to your theory. And then based on that, then you go and have a look at the answers. So for example, when you read that TA is a tangent to the circle, you immediately start thinking about all the things that you know about tangents. Okay, so for example, the first thing that would come to mind when you see the word tangent is you would think to yourself, tan chord theorem. Okay, or you could think tangents from the same point are equal. Or you could think about radius perpendicular to tangent. Okay, so you read the information and you make the connection to the theorems. All right, because those are the things that are going to help you to get to the answers. The other thing that they tell us here is that M is the midpoint of chord PT. So M is the midpoint of chord PT. So now, again, this relates back to what I was just talking about. Okay, so we've got a line from the center, OM, to the midpoint of the chord. All right, so straight away, does it come with a 90-degree angle? No, it doesn't. Okay, so here our connection is to line from center. And I hope you're all thinking this as I'm saying it, to midpoint of chord. Okay, line from center to midpoint of chord. So it's always a case of reading the information and relating it back to the theorems that you know. The center of the circle is O, so another piece of information. Right, so if they give us the center of a circle, there's lots of places that we can go. Angle at center is twice angle at circumference. Our chord theorems. What else involves the center of the circle? So here, line from center, sorry, angle at center equals 2 times angle at circumference, etc., etc. Now some sort of slightly less useful information. But when I say less useful, I don't mean that we're going to ignore it, but PR is produced to TA at A, and TA is perpendicular to PA. So again, when they tell us TA is perpendicular to PA, it means there is a 90-degree corner over there, and we can see that they've drawn the little box for us. Then they tell us that T and R are joined, OR and OT are radii. So if they tell us OT and OR are radii, why would that be important to us? OT and OR are radii. Why would they tell us something like that? They're equal, absolutely. Radii are equal to one another. So often what happens is that radii are used together with a chord to make a triangle. I'm going to rub it out, but look here. Okay, can you see there's the one radius, OT. There's the other radius, OR. Can you see that it makes a triangle with chord TR? Okay. There we go, Nolwazi. So often in these situations, maybe not this particular situation, but often in these situations, because we have got two sides that are equal, we're going to have angles opposite equal sides. So that's another throwback from all the way back from grade 8. I don't necessarily mean it in this particular question, but always be aware of angles opposite, whoopsie, equal sides. I wrote that very badly. Let me just correct that. Angles opposite equal sides. Okay, so that's something that comes up a lot for us as well. Okay, so first things first, prove that MTAR is a cyclic quad. So if you are doing paper 2, they should give you an answer book, which means you should be able to use colored pens or highlighters. Go and highlight the quad that they're asking you to prove is cyclic. So MTAR is this one over here. Okay, so if we prove that it's cyclic, or when we prove that it's cyclic, we are proving that it is possible for us to draw a circle through M, T, A, and R. Not that there necessarily is one there, it is possible for us to do so. So going back, we've got to think of, okay, either converse opposite angles of a cyclic quad are supplementary, converse exterior angle of cyclic quad, or converse angles in the same segment. In this particular example, there is no bow tie inside. Okay, so if there's no bow tie inside the would-be cyclic quad, you cannot use converse angles in the same segment. All right, so if there's no bow tie, I'm just going to put this on the side for you. No bow tie inside cyclic quad. That means you cannot use converse. My spelling is atrocious today. Sorry, guys. You cannot use converse angles in the same segment. Okay, so being able to prove a quad is cyclic is also related to being able to look at your information and decide what isn't appropriate. Okay, so in other words, if there's no bow tie inside, we immediately ditch converse angles in the same segment. That helps us to narrow our focus. So now we're thinking either proving that the opposite angles are supplementary, or we're looking for an exterior angle. Okay, so in this particular case, both of those will work for this question. Okay, the exterior angle of the cyclic quad, look for something that's named. If it's not named, then you're probably not going to use it. Okay, if it is named, then you probably are going to use it. So, for example, if I have a look at an angle that's not named, this little angle over here, OTM, is not named. All right. They haven't called it T1 or T3 or anything like that. So I'm probably not going to use it. I say probably not. Okay. So look for things that are named. So highlight, look here. We are extending side TM, and look there. We have an exterior angle. If I can prove that M1 equals A, the opposite interior angle, I've proved that the quad is cyclic. Okay, so now I've got to go back and look at the other information on the diagram. If this is true, what do I know about M1? So you tell me, sorry, I've done so much talking this lesson, you must be so sick of listening to me. What do you know about M1? There we go, Nolwazi. So RMT, let's just have a look at this. RMT is 90. Or OR cuts TP in half. Therefore, A1 plus RMT. Exactly. All right, that's lovely. That's lovely, Nolwazi. You've seen that beautifully. Okay, so I'm going to put that down on paper for you. Okay, so here we can use converse exterior angle of cyclic quad. This is how we have to set it out. When you are doing geometry, you are telling a story. Okay, so it has to have an introduction, it has to have a body, and it has to have a conclusion. You are telling a story, and it has to be in the correct order. Okay, so for example, if you were going to go swimming, all right, first you would need to get to the swimming pool. Then you would have to put on your swimming costume. Then you would jump into the water. Okay, you can't jump into the water if you're not at the pool. You're not going to jump into the water if you're not wearing your swimming costume. Okay, so things have to happen in a logical sequence like a story. So the first thing that we need to establish here is why M1 is equal to 90. That's our introduction. Then once we've established that M1 is 90, we can conclude that it's equal to A1 that's also 90. And then we can say, this is why it's a cyclic quad. Now we're trying it all together. And then our reason, converse exterior angle of cyclic quad. Okay, I hope that makes sense for you. I have said that quite quickly. All right, so the first thing that we would write here, matrix, is that angle M1 is equal to 90. Goes back to this first piece of information that we were talking about, line from center to midpoint of chord. So line from center to midpoint of chord. Okay, that's our introduction. Now we know that A1 is 90 because that has been given to us. A1 equals 90. Given. So now we link the two together. Therefore, M1 equals A1. Very important. Okay, it's because M1 equals A1 that the quad is cyclic. So you have to say that. So therefore, MTAR is cyclic. And our reason, converse exterior angle of cyclic quad. Okay, now there is another way that you can do this particular question, and I do want to do it with you very quickly. All right, so we could also work with M2 and use converse opposite angles of a cyclic quad are supplementary. Okay, so by the same vein, I can say M2 equals 90 for the same reason. Line from center to midpoint of chord. Okay, then again, I conclude A1 is 90. Therefore, M2 equals a 1. Let's just scooch down a bit. Therefore, MTAR is cyclic, and my reason, converse, opposite angles of cyclic quad are supplementary. Okay, matrix, how are we feeling? Does that help? Yeah, it is actually supposed to be that simple. Okay, good, lovely. Good. Okay, so I'm in the middle of telling you a story about Euclidean geometry. That's the grade 11 stuff. Let's go back to over here. All right, so there's an example of how you would prove that a quad is cyclic. All right. Where were we? Okay, and then your tangent axioms, theorems, and converses. Here we are talking specifically about tan chord theorem. Okay, so when it comes to tangents, we are talking about tan chord theorem. We are talking about radius perpendicular to tangent. We are talking about tangents from the same point. And we can also, I suppose, bring in here converse tan chord theorem. I'm so glad for you. That's the whole idea. That's why, you know, I wanted to do a lesson like this, because I found with the matrix last year when I had the opportunity to do that with them, there were also a lot of light bulb moments, especially when it came to trig. So, oh, Tando, that's a very sweet thing to say. Thank you so much. The boys in my class do not think so, I can assure you. But thank you. I appreciate that very, very much. It's always lovely to be with you guys as well. I thoroughly enjoy these lessons, which is why I keep coming. Okay, so let's move on to the matrix stuff. That's the grade 11 stuff. So when it comes to proportionality intercept theorem, we need to know proportionality intercept theorem, and we need to know converse proportionality intercept theorem. The other thing that we need to be aware of when it comes to our tangents, yes, or you must either have proved, or you may need to prove that a line is a tangent. Okay, but yeah, you would need to establish that they were both tangents first. Okay, so in geometry, there's a way of working forwards, and then there's always a way of working backwards. So for example, when we have got the angle between the tangent and a chord, we can use tan chord theorem to establish that the angles are equal. Then we can work backwards. So if we can establish that, you know, an angle is equal to another angle, then I can work backwards and I can establish that a line is a tangent to a circle, for example. So that would be its converse. So working forwards is the theorem that you get taught. Then the converse allows you to be able to work backwards. So converse tan chord theorem proves that a line is a tangent to a circle, for example. Okay, so same with proportionality intercept theorem. Proportionality intercept theorem tells us that a line drawn parallel to the third side of the triangle cuts the triangle into equal proportions. If I know that a triangle is cut into equal proportions, then I can work backwards and establish that that line is parallel. Okay, so let's just go and summarize that for you guys as well. So when we're talking about proportionality intercept theorem, the diagram will come with a line drawn parallel to the third side. So they will tell you that this line is parallel to the third side of the triangle. Okay, so if this is A, B, C, D, E, you are given that EB is parallel to DC. Similarly, the conclusion, or what we would then say, is that AE over ED equals AB over BC. Proportionality, intercept theorem, and you must name the parallel lines. Okay, if you don't name the parallel lines matrix, you are not going to get the reason mark. Okay, so geometry, all geometry, whether it's grade 11 or grade 12, is marked statement, reason. Or if it's like something like from grade 8, so like angles opposite equal sides or angles of a triangle add up to 180, then they could just give you one statement reason mark. Okay, for both. Yes, Lebogang.
Ma'am, regarding the theorems, now do we also still need to know how the formal proofs of the theorems?
Yes, yes. So you need to know the formal proofs of the grade 11 theorems and your 2 grade 12 theorems as well. Maybe what I should do is speak to Watobe and see if I can do a lesson on those at some stage. Right, but yes, you would need generally the ones that get asked. So proofs of theorems. I know there's so much, isn't there? There's just so much for us to learn. So proofs of theorems, the ones that you're expected to know. Sorry, I'll go back to. So proofs of theorems, the ones that you are expected to know that come up sort of regularly would be angle at center equals 2 times angle at circumference. Now, your teachers should have told you whether they are testing proofs or not. You want me to do the proof of the proportionality intercept theorem? I don't mind doing that for you. That's fine. The other one that comes up as well is that the opposite angles of a cyclic quad are supplementary. Is another one that you must learn. The other grade 11 that comes up often is tan chord theorem. So these are the grade 11 ones that they ask in grade 12. That are quite common. And then you need to know how to prove proportionality intercept theorem. And then the fifth one that you need to know is how to prove the similarity theorem. Okay, those are the grade 12 ones. Okay. Tsegofatso has asked if I do the proof of the proportionality intercept theorem. How do the rest of us feel? Is this something that you want me to go through now? I'm not sure if it would be asked in your June paper. What's the sort of general consensus on that? So someone says yes, yes. How are the rest of us feeling? Yes, yes. Okay, there's lots of yeses. Okay, all right, that's fine. Let me just grab the diagram because that's going to be easier than me trying to redraw. Let's just find. There we go. Just give me 1 second, Matrix. I won't be long. I'm just going to grab the diagram. And I'll go through the proof with you. I don't know if there'll be time today for me to do the similarity proof, but I can always do that with you guys at some stage as well. Okay, we're nearly there. Come on, textbook. All right, so what they will do is they will give you, let's just cut and paste this. they will give you a diagram. Okay, and the question will say, generally where this question comes in is you will be asked a little bit of grade 11 work, and then they will give you the proof, and then all the grade 12 work will follow after it. It'll be a question on its own. So they may say something like, use the diagram below to prove that AD over DB equals AE over EC, for example. Right, so you'll recognize that. Amahle, I'm going to try and finish this one in time. We should be okay with this. But yeah, we've stayed an extra half an hour, so we've got 15 minutes to go. Okay, so I'm just going to write here so that when we come back, if you want to come and watch this video again, so proving proportionality intercept theorem. Okay, so the only time that you are allowed to do any constructions in caps is when you are proving a theorem. Okay, other than that, we do not do constructions. Okay, you're also allowed to do a construction in analytical geometry if you have got let's say if you need to connect 2 points to make a right angle triangle. I did show you guys that when we did the analytical geometry course. Okay, so you have to write that you are doing a construction. Okay, so in a situation like this, you would then have to say that you are constructing height h and you are constructing height k. All right, so you would say construction. Okay, so in other words, you would draw, let me get a ruler from E like so. Construction. And we would obviously have to give that, or we would just have to state that it was perpendicular. Okay. And we're going to call that H. And then we would also have to construct K that is perpendicular to AE. And then maybe I should have done that in a different color, but anyway, it doesn't matter. And then you are going to do another construction from D to AE, and we're going to call that line over there K. All right. So now we're going to work with the area of the triangles. So the first triangle that we're working with is the area of triangle ADE. So we would take the area of ADE and we are going to divide that by the area of triangle BDE. So when we're talking about that area of triangle ADE, it's this one over here up at the top. BDE, oh yes, sorry, we need to do 2 more constructions. Sorry, beg your pardon. So we also need to construct, a line from D to C. And we also have to construct a line from B Let's just see if I can move that one. It's supposed to be, oopsie. Okay, let me delete that and do it again. Let's draw it a little bit better. Oh, why does it start out there like that? Stupid thing. Okay, so anyway, I'm not going to waste time with this. This point over here is supposed to be at B. Okay, so construction of H perpendicular, and then the other thing is we have constructed B, E, and D, C. Okay, so when we're talking about the area of triangle ADE, it's the triangle at the top. Triangle BDE is this triangle down here at the bottom. Okay, so we're going to use half base times height. So for triangle ADE, we would say half AD times H. Okay, so this is going to be half AD times H. Everybody happy with that? For triangle BDE, we are going to say half BD times H. Okay, now this is the bit that might be a little bit difficult for you to see. Okay, so think about it like this. If I have a scalene triangle, hang on, let's draw a scalene triangle this like this. What you can do is that your height, your perpendicular height, does not necessarily need to be inside the triangle. But if this is your base, then your perpendicular is dropped from the vertex perpendicular to the line that forms your base. That's what's happening with triangle BDE. Okay, so BDE is this triangle. I don't want to actually draw on this to make it confusing, but BD is your base. And then the line from E, perpendicular to AD, that is your perpendicular height. Do you see that now? Does that make sense to everyone? Okay, so the perpendicular of BDE lies outside of the triangle. Is everybody happy with that? You see it now? Okay, so BD is the base. Okay, the vertex is E. So it's like E is up here, and B or that would be D and B are over here. This is H. It lies outside of the triangle. Okay, cool. All right, good stuff. And we know that when we divide anything by itself in maths, we're going to get 1. So that's where we get AD over BD from. Right. Now we're going to do the same thing. Okay, we're going to work in triangle ADE and CED. Area of triangle ADE and area of triangle CED. And again, we're going to use half base times height. So when it comes to ADE, okay, we're now looking at AE as the base. Okay, so in triangle ADE, we're now considering AE as the base where the perpendicular height is K. So that's going to be half AE times K. All right, so just scooching up again, there you can see that AE is now the base. So in the first bit that I was writing, I was looking at AD as my base. Now I'm looking at AE as my base. Again, can you see triangle CED? Can you see that its perpendicular height also lies outside the triangle? Okay, it's line K and it's perpendicular to line AEC. Okay, so this is going to be half EC times K. Okay, EC is the base now. All right, and again, we would cancel out. So we would divide a half with a half and k with k, and we would get AE over EC. All right. Next thing that is important is that the area of triangle BDE is the same as the area of triangle CED. Okay, that is because triangles that have the same base and perpendicular height when they lie between parallel lines. Okay, so the area of ADE over the area of BDE equals the area of ADE over the area of CDE. Okay, so just here on the side for you, triangles that, I don't know why my pen sometimes does stupid things like this. Triangles that have the same base and height, so perpendicular height between parallel lines, have the same area. Okay, so that means we're now at the end. Therefore, we're allowed to conclude that AD over BD equals AE over EC. Okay, so that's how it goes. You've got to name the constructions that you've done, and then which triangles you're working in. The areas are the same, so that's why AD over BD equals AE over EC. Okay, and remember you are given that these lines are parallel. So it doesn't say it on the diagram, but it does say over here that those lines are parallel. And that is the proof of the proportionality intercept theorem. Okay, cool, Tsechofatso. I think having someone point this out to you over here helps a lot, doesn't it? To understand which triangle we're talking about and what's the base and which line is actually the perpendicular height. Okay, I think that's really critical there. Okay, cool beans. So so you're happy. Amahle, I see you said there was something you didn't understand. Do you want to ask any questions, Amahle?
Yes, I do, ma'am. Good evening.
Good evening.
The second like area, the second area calculation where you say area of ADE over area of triangle
CED.
CED. Could you please just explain that part, because I understand the
Okay.
bottom part and the first part.
All right. So when you are doing this first one where I'm putting the pink arrow, it's because you want this side over here, BD. That's going to be your base. Okay. So now when we change our perspective and we're talking about triangle CED, then we want this line over here, EC, that is our base of our triangle.
Yes.
Okay. So your triangle is located here. There's DC and there's DE. So there's your triangle.
Yes.
Here's its base. So this line over here is its perpendicular height. Okay.
Oh, okay.
So in other words, if I redraw that, I've got C over here, I've got E over there, I've got D right above over here. Okay. And then my perpendicular height is the line K. which is somewhere over here.
Yes.
Okay, that would be your
Yes.
perpendicular line. So again, it's this situation over here where your perpendicular height lies outside your triangle.
Okay.
Okay, your perpendicular height lies outside your triangle.
Okay. Okay. Thank you, ma'am.
Okay, all right,
Thank you.
that's fine, no problem.